For the introduction. It's been a while since our last webinar, so I would like to personally thank you for joining us again. SIMetrix SIMPLIS version 8.4 was released on May 19th, and included with its release is a lot of new developments. Because of that, the next 5 months worth of webinars are going to focus on the new features of version 8.4. This month will focus on the ease of content creation and usability development items. The following 4 webinars will be on the larger development projects. Now, those next 4 webinars are going to include the one in July, which will be the first part of a 3-part series of the SIMPLIS magnetics design module, and it will focus on inductors.
Muted.
The following webinar will be held in August, and that will be a part 2, and that will focus on transformers. Then we'll take a break from the SIMPLIS magnetics design module in September, and we will talk about modeling digital content with a SIMPLIS DLL defined device. And then finally, in October, we will revisit the magnetics design module, and we'll actually use an application to show the power and the use of the magnetics design module. So for today's webinar, what we will cover is shown here. First item we're going to talk about is the capacitor or inductor conversion tool. Then we're going to talk about the introduction of power supply sources and loads. Then we'll talk about 2 useful schematic editor features. Then we'll talk about the updated controlled sources with ideal limiting outputs. Next, we'll talk about the new multi-level Lossy transformer. And then the last 2 items will be brief overviews, the first one being the magnetics design module, and the last one will be the C-code DLL defined digital devices. So first item we're going to talk about is the capacitor or inductor conversion tool. Currently, the way you define a piecewise linear capacitor in SIMPLIS is by using its charge versus voltage characteristics. Now, if you don't have those characteristics readily available and only have capacitance versus voltage, which is normally what you have, you must use a separate spreadsheet tool to derive the information needed. With this new tool, you can enter the capacitor's capacitance versus voltage and end up with the piecewise linear capacitor defined in charge versus voltage that is ready for SIMPLIS simulations. So let's go ahead and take a look at an example here. So this is our standard self-oscillating circuit converter. It's a flyback converter. And what I want to do is I want to take a look at this capacitor right here. This is a piecewise linear capacitor. Now, normally you would have to enter this voltage versus charge information right here. But in this case, what we now can do is enter our capacitance with this new tool button right here. And this brings up our conversion tool. So on the left-hand side, you have your capacitance versus voltage input. And on the right, you have a charge versus voltage input. Now, what we can do from here is when you, let me go ahead and drop a standard one here. I'm going to do piecewise linear capacitor. Just searched it. Now, if I were to, this is the standard default options. If I were to enter this capacitance here, you'll notice that is populated on the right-hand side. What we can actually do with this information is work in a right-to-left fashion, or we can enter the capacitance versus voltage and work from a left-to-right manner. So with the voltage versus charge information, we can click this left-hand button, and now this will give us the step capacitance, the piecewise step capacitance of this information right here. Now, this is a linear curve, that both the segments are the same, so you have the same capacitance. There's no change. But what we can now do in this tool is we can utilize the SIMPLIS SIMetrix digitized datasheet curve function. Now, this is only This function can only be used with a pro or an elite license, but if you have a base or a non-pro or elite license, then you can still have access to enter the capacitance versus voltage by hand, but you can't use the digitized datasheet curve. So I'm going to go ahead and click on this, and this brings up it begins the normal digitized datasheet curve tool, and I have an example right here, an example datasheet curve. So I'm going to press open, and this is the normal digitized tool. So I'm going to check that my bounds of my graph are found, which they are. So I'm going to go ahead and press continue. Now what I have to do is add points along my desired line. So I'm going to press along the line here. Alrighty, and I'll hit continue. And now I have to tell its minimum horizontal axis value, which is 0, and the maximum, which is 30. And that is not logarithmic. And then my minimum vertical axis, which is 0, and then that is 6 millifarads. And then again, not logarithmic. So I'm going to hit complete. And now my curve has been digitized here. You can see we have over 500 points. That goes from 0 all the way up to 30 volts. Now from here, what we can do is, or what we need to do is we need to find the curve fit, or we need to find the charge and then curve fit to get the best result. So what I'm going to do is click this right button to digitize, or excuse me, to find the right voltage versus charge segments. Now what we can do from here is we can change the number of segments, piecewise linear segments. So if I go down to 2, and I'm going to turn off this limit so that way it uses the full 30 volt, right? So it gives us a better look. What we can do now is we can plot the piecewise linear characteristics. Now we can see that up top we have the blue capacitance curve, it's what we just digitized. From that curve, we then take the integral of this curve, of the charge curve, or excuse me, the capacitance curve, to get the charge curve, and that's the blue at the bottom. So that's charge versus voltage. Then what we do next is we piecewise linear curve fit the charge versus voltage, because that's what SIMPLIS cares about. And then finally, from that charge piecewise linear curve, we then extract what the step capacitance will be. All right. Now we can see that the piecewise linear curve isn't the greatest. It's good, but we could have better. So what we're going to do is add one segment to have 3 segments. And when we plot that again, we can now see that we are much closer, much better curve fitted. All right, so from here, I think I'm good. I'm going to go ahead and press OK. And now all of that information is placed into this charge versus voltage table. And when I hit OK, it now updates there. And we now have our simulation that has our new defined, or our piecewise linear curve fit based on our simulation graph, or excuse me, our datasheet graph. All right. Alrighty. So now if you go back into this tool as well, it'll save everything you've done, so you can come back in and again, you can now take this information and you can press the left button and it'll give you the step capacitance. So our first step is just about 3.5 millifarads, drops down to 1 millifarad, and then 231 microfarad. Alrighty. Now this is just this is an example with the capacitor. Now the same type of logic can be used to apply this to a piecewise linear inductor. So therefore, we can take this tool and use it to grab the inductance versus current characteristics and convert it to a flux linkage versus current defined piecewise linear inductor. Because SIMPLIS needs flux linkage versus current, not inductance versus current. So we can see that shown here if we come over to this magnetizing inductance of this transformer. If I go ahead and open this up, this is a normal piecewise linear inductor. And again, you can see this now enter inductance button. The information was populated here on the right, and if I click left, it will now show the stepped inductance of that inductor. 4 millihenry, 1,000 or 1 millihenry, and then 100 microhenry. Right? And you can also, again, you can plot this. Now this is because we just input this information. It doesn't have the stepped or the non-stepped or the exponential graph that you would expect to see because that information doesn't exist. Alrighty. So that is the first tool. Next, what we're going to talk about, let me go ahead and close this down here. Next item we're going to talk about is the newly introduced power supply sources and loads. First item we'll talk about is the sources. This slide shows all of the possible sources that are now available. You can see on the left there are 6 AC line sources, and on the right you can see that there are 12 DC sources. Now, every single one of these sources contain internal voltage and current probes, each with selectable measurements. So let's go ahead and take an example. We're going to come back to our self-oscillating circuit, and we're going to manipulate this one so that way we can see these new sources and loads in action. So I'm going to go ahead and run the simulation again just so we have a baseline. Alrighty. Now I want to input my source. So right now I just have a 310 volt DC source. So I'm going to come up to my part selector, come down about halfway, you'll see this power supply sources tree item. Now we have these separated in 2 separate items. We have our AC sources and then our DC sources. So because we have a DC source, I'm going to put a DC source. All right. So from on the left, it's broken up into the different types of sources. We have our DC source, just a normal DC input source, right? That's looking for a DC voltage. But we also have it broken up into some smaller categories as well. We have a small signal source, which this one is extremely powerful. This is our DC input impedance source. So if you place this down, or if you place this, make this the active source, you can measure the input impedance of your circuit. We also have single event sources like our ramp input source, if you wanted to do like a soft start. And then we have some periodic sources as well. So these single event obviously happen only once, like a ramp or a pulse. And the periodic sources will repeat, like a square wave or a pulse input wave. All right, so I'm going to keep this as a DC input to make it the same. And our input is 310 volts. So I'll leave the source resistance there. That's fine. And hit OK. And I'm going to just drop this down, and I'm going to delete my old one and replace this one. And I'm going to go ahead now. I'm going to open this back up because I forgot to point out at the top here, or on the right side, we have all of our parameter inputs like our voltage, DC voltage, and our source resistance. But we also have some probes as well. These are the internal probes. You can turn them off or on, and then you can manipulate however you want them to look. But we can also add probe measurements. So if I click on this, we can now have our built-in measurements here. So for my input voltage, let's say I'm going to do my, it's not going to change much because it's DC. So let me go, I think it would make more sense to add it to a current probe. Again, you can enable or disable. And now we can add a current probe measurement. And I'm going to do just a maximum current measurement. All right, and then hit OK. Now to accompany these sources, we also have created a wide array of loads. Now this slide shows all the possible loads. All of these loads can mimic DVM in that they can have 2, 3, or 4 terminals. We have, and just like the sources, all of these contain internal voltage and current probes, each with selectable measurements. So we have a variety of steady state and small signal loads on the left. And then on the right, we have the transient loads, and we'll go ahead and drop one down and kind of take a look at that. So I'm going to come over to my load here. Now my load is just this resistor here. So I'm going to go ahead, or let me go ahead and drop a load down first. So in the part selector just below the power sources, you have your power supply loads. And this is the only option here. So we're just going to go ahead and double click that. And for our loads, we can see we have our steady state loads, which are just a resistive load or a current load. We have our small signal loads like our Bodie plot load. And we also have an output impedance load, very, very well sought after load, if you will. Then just like our source, we have our single event loads like a ramp load or a short circuit load. And then we have our periodic loads such as a square wave form or a pulse load. So because I am going to replace a resistive load and a Bodie plot, I'm going to go ahead and drop a Bodie plot load. And my load resistance currently is 2.5, so I will change that to 2.5. And in just like the source, I can add voltage probe measurements. So I'm going to add a peak-to-peak voltage measurement, and that's right here. And just in the current probe, we can also add let's do a maximum current here. And then because this is a small signal load and there is a Bodie plot probe within the load, we have options to change this as well. So what I'm going to do is I'm going to change my single grid to be 2 grids. And you can also add gain and phase measurements, gain measurements on the left and phase measurements on the right. Okay, so this should be ready to go. One final thing to note is that you can change the number of pins up here at the top. Now our small signal load, our Bodie plot loads require 3 pins or more, but if you change this to just a normal resistive load, you would see that you can have the 2, 3, or 4 pin option. All right, so I'm going to drop this here to the side, and I'm going to delete my row, or excuse me, my resistor. And because the Bodie plot load has the Bodie plot probe and the perturbation signal, I'm going to delete these as well, all down here. All right, so now I just need to wire this up. And I'm going to press my F6 to swap and drop it right here. And then I drop my sense pin here. All right. So now we should have the same exact circuit as we did before because we did a 1-to-1 swap. I'm going to run this simulation. See what happens. All right. So now we have our new tabs because we've added new probes, if you will. This is our source current and voltage probes, and you can see our maximum current measurement. And then here is our load waveforms, and you can see our maximum current and our peak-to-peak voltage. And then this is our new Bodie plot probe, which if we jump back and forth between our old one, you can see they line up very well. And that makes sense because we haven't changed anything. Right. So from here, what we can do is exploit the fact that these sources and loads look very familiar if you are familiar with the design verification module, or DVM. So what we can actually do is select both of these, source and load. If we right click, there's this option right here to upgrade to a DVM source and load. So if we click on that, it's going to output on your in your command shell what it's actually doing. It's changing some parameter names and parameter values to get it ready for DVM. But now that we have a DVM source and load, we can now run, or excuse me, we're at one step closer for DVM. So from here, all you need to do is drop a full power assist probe. Then we would update our information in here. We have, you know, our 310, oops, 310, let's say 300 and 320, and then our output is 5 volts, 2 amps maximum. Okay, now from here, we can just run DVM, no problem. So we can built-in test plan, DC to DC. And I'm just gonna do a 50% Bodhi plot. See what shows up here. So now you can jump back and forth between your DVM schematics or your DVM simulations and your non-DVM simulations. And if I come back to here, now what I can do is I can select both of these, source and load. If I want to run some, if I wanted to now run an impedance or a, a different type of step, I can downgrade it. We change the symbol so you know what it looks like. And now we can change these again to have, a ramp output or a different type of input and output. All right. One more note on the sources. If you, let's say you dropped a DC source and you realize later that you need an AC source, well, we have this handy little button here where you can now enable the AC line sources, and that gives you a fixed input, just a normal sinusoidal, or there's startup. Another helpful one is your dropout, line dropout, surge sag, and a really cool one, the glitch input source, where you can use to mimic like a lightning strike or something like that. All right. So next, if there are no questions, I'm going to go ahead and move on to the next item, which are 2 useful schematic editor features. Now, the first one is the disable short circuit component. Now, in version 8.3 release, we introduced a feature that allowed you to remove a component from the schematic to leave an open circuit. Now with version 8.4, we've added a similar feature called the disable and short circuit component feature. When applied to a schematic symbol, the simulator will remove the instantiation from the netlist or the deck and replace it with a short circuit. So let's go ahead and take a quick look at that. I'm going to come to this guy right here. So this is just a simple voltage divider circuit. And what I'm going to do is I'm going to run this. So what we should see is a 5 volt in series with a basically 2 kilo ohms, which would give us a 2.5 milliamp current. Nothing special. Now what I want to do is I'm going to select R2. I'm going to right click the device to bring up the context menu, and I'm going to do the disable and short circuit selected. Okay, so now you can see it's grayed out because it is disabled and it is short circuited. So now if I run the schematic, what I should see is a 5 volt in series with a 1 kilo ohm resistor, which that's what we do. We see 5 milliamp. Makes sense. Now this is a powerful tool, but it can be dangerous. You have to make sure what you're doing, first of all, makes sense, and that it doesn't prevent the simulator from simulating. And what I mean by that is if I were to disable or short R2 and short R3, now what should happen? If I I'm going to get an error. Well, the reason is because I am now shorting a voltage source by 0 ohms effectively to ground. Do that in real life, you're going to see some smoke. Do that in SIMPLIS, you're going to see an error. Same difference, right? So you got to make sure that whatever you're doing, it is going to still allow the simulator to work. So let me go ahead and close this. Aside from the context menu, which I just showed you, this feature can also be implemented using the set disable command. This is a script command. The first argument to the command will be the property name. So in this case, it would be ref. The second argument will be the property value used to identify instances to process. So in this case, we want the reference with R2. And then the last argument will determine the action to perform. So either short or enable. There's short here and enable here. So obviously the short will short the component out and enable will enable the component. Right. What this does is it will allow you to automate this with a preprocessor script used in DVM. Okay. Now, by default, all 2-pin symbols will work without intervention, but some symbols or symbols with 3 or more pins need some additional configuration. That's done by the way of a symbol property named short pins right here. Okay, so let's take a look at how this is done. So I'm going to come to 4 here. All right, so this is just a voltage controlled voltage source, nothing fancy. And what I'm doing is I am gaining a 5-volt source by the factor of 2 across, just a 1 ohm resistor. So what I should see when I run this simulation, I'll do that right now, is I should just see a 10-volt output, which that's what we have here. Okay. But now if I go ahead and I want to short this, if I come context menu and disable, it has too many pins. It has more than 3 pins, so it's going to give me an error saying that it could not, E1 could not be shorted because it has 2 or more. And so that's when we need the short pins. Okay, now you notice there's a big 1, 2, 3, 4. What this is, and I'll show you, I'm going to edit this, I'm going to look at the symbol, and I'm going to look at the pin order. So what those big numbers are saying is the pin order, right? Pin 1 is the P, or the positive output. Pin 2 is the negative output. Pin 3 is the controlling positive, and pin 4 is the controlling negative. That's just here for our visual purposes, right? So 1 positive, 2 negative, 3 controlling positive, 4 controlling negative. Okay, what I want to do is I want to add this short pins property. So I'm going to right click, select the symbol, right click and edit add properties. And from here, I'm going to add a property called short pins. Hit OK. Now, the way we use this is we want to do the pin. So if I wanted to short pins number 1 and 3, I would do 1-3. And if I want to short multiple pins, I'm going to concatenate them together with commas. So I want to short 1 and 3, and then comma, pin 2 to 4. All right, just some house cleaning so we can see it nicely. All right, so now I have my new short pins property that's going to tell the system to short pins 1 and 2, or excuse me, 1 and 3, and 2 and 4. And I'm going to go ahead and see if this works. All right, so now it works. We have our shorted. So now what we should see when I run the simulation, I should see no gain. I should just see a 5-volt output. So let's go ahead and check that. And our new output is 5 volts. All righty. So that is the shorting. So now we're going to talk about the second feature that has been added, and that is the component insert. This easy insertion tool will work on any two-terminal component. Basically what it's going to do when you place a two-terminal symbol on any wire, the wire will automatically split and create that division there. All right, now I'm going to come back to our short pins here. Now say I wanted to just place a capacitor or another resistor. If I were to place, select it to place and drop it on this wire right here, we can see that it removes the wire in between the two pins. Now there is a note that this will only work when placing a new component and not when you try and, if I were to try and Control-C copy, Control-V, you'll notice that the wire is still shorting out that resistor. So it only works when placing new components and not copying and pasting existing ones. Alrighty, so that simple one, so we won't spend a lot of time on it. Next, we're going to move on to the updated controlled sources with ideal limiting. Right. Previously, when the gained input signal of a controlled source with ideal limiting drove the output into the clamping condition, there would be a slight slope. In most instances, this was not noticed. The slope was very, very small. However, it was more apparent when the gain was very large. The new controlled sources have the option for actually ideal limiting to eliminate this slope. And we'll go ahead and look at an example of this. So what I'm doing here in this schematic is I'm taking a negative 20 volt to 20 volt ramp, or a step ramp on the input, and I'm gaining that by 10,000, and I am limiting the output to be between 2 volt and negative 2 volt. All right, so you can see that this is non-ideal. This is the old version, and we even give you a little hint on the symbol as well, where you can see that there is a slight slope. And I'm going to run this schematic as is. All right, so what we're looking at in the graph is on the vertical, on the y-axis is our output voltage, and on the x-axis is our input voltage. So we are going from negative 20 to 20, and we're trying to clamp at negative 2 on the output and positive 2 on the output. But you can see, because there is a slight slope, that there is not a truly limit or clamp happening. So what we can do here is we can open up this, and we are going to turn on the ideal clamping for 8.4 and above. And what we do is we change, now we can see the new symbol that has no slope, and we have an ideal number right here. And when I go ahead and run this simulation, you can now see the dramatic difference. With the new version, we are truly clamping at 2 volts, or yeah, negative 2 volts and positive 2 volts. All right, let me go ahead and close this down. If there are no questions, I'll go ahead and move on to the next item, which is the newly added multi-level lossy transformer. Now, the multi-level lossy transformer can have up to 20 total windings and has 4 levels of complexity. Here is an overview of the levels, but we'll walk through each one in the following example. This is just here for your reference. All right. Again, we come back to our flyback controller here. We use this one quite a bit. And for this example, since the DC transformer, the existing DC transformer, does not have a way to store any energy, what we typically do is add an inductor here to depict the magnetizing inductance referred to the primary windings. If you have taken our Advanced SIMPLIS training, you will be familiar with this concept as we discuss it during the course. Now, with the multi-level Lossy transformer, we've incorporated the magnetizing inductance along with the winding resistance here, here, and here, and any leakage inductance down here. Okay, so let's go ahead and I'm gonna open this up. This is our new multi-level Lossy. Now you can see the difference between the two. The old version, the circles are not colored in, and the new one are colored in, and there's 3 levels or 3 lines between the windings. So I'm gonna open up this one. Model level 0 is our just the DC transformer and linear magnetizing inductance. So you have one level, one linear magnetizing inductance. Model level 1 changes that inductance to be piecewise linear, right? So we can now define our piecewise linear inductance. Model level 2 has the piecewise linear magnetizing inductance, but we've also now added our leakage inductance with the shunt resistor and our primary windings. So our we have 3 windings because we have a primary and 2 secondaries. Now, model level 3 is used with the magnetics design module, and we'll talk about in a few minutes. So if I come back out here, I'm going to hit cancel. If you notice, we do have a piecewise linear inductor for our magnetizing inductance. So what I'm going to do is I'm going to turn on my model level 1. All right, now this you may or may not notice, but this is the same exact inductance characteristics as the previous one. So I'm going to press OK here. And what I'm going to do is I'm going to replace the 2 with our new, hold on, let me do this first. Let me just give it a simulation so we can see. All right. So this gives a nice load step transient. And now I'm going to replace our existing items with our new one. All right, now this is a level 1, which is the same with the same magnetizing inductance. So what we should see is the same exact simulation, which we do. Now next, what we can do is we can up this to a model level 2, which includes all of the Lossy items. Now what we can do, that includes the winding resistances and the leakage inductance. So we'll use our new disable and short circuit, the selected tool. And again, this should all be the same, which it is. All right. So now from here, what we can do is we can take it a step further and look at our model level 3, right? Now, before we do that, I'm going to come back to our slides here. All right. So our magnetics design module, also known as MDM, is a separate module that can be added to any version of SIMetrix SIMPLIS, that is Classic, Pro, or Elite. With MDM, you can create a very accurate model based on the physical construction of the magnetic device. Now within MDM, there is you can create both transformers and inductors. And in our case, what we've done is we've created our transformer, and I'm going to open MDM here by clicking this Edit with SIMPLIS MDM. All right, so this is our MDM. Now what you can do from here is on the left, the top left, is you can select or pick your core. These are all available, a large library of predefined cores, right? And as you pick different ones, you can actually see the updates on the right. And then at the, we have all these different types of cores. We even have some different vendors that provided core libraries, and they're included as well. Once you select your core, you can choose your core material from the bottom here. So we have ferrite and powdered iron, which are probably you're most familiar with. All right, so once you've selected your core and your material, you can now change your windings. All right, so in the windings we have, you can change them for each individual leg of your transformer. So in our primary, or only primary, you can now change your wire gauge here, and you can actually do this on the fly. So if I were to say, this is built with the 17 gauge, if I were to say, okay, what does a 16 gauge looks like? You can click on it, and then you can immediately see that we are now outside of our winding window, and it won't work with this, okay? You can also add any taping that you have. These darker gray, that's our tape. And you can also change the type of wire for each one as well. Right. Finally, what we have is a cooling tab. Right. In the cooling tab, you can choose your cooling concept, whether it's natural, forced, or no thermal modeling at all. And what is also neat is you can actually choose the sides that are available for convection. So if you don't have any top convection, then you can turn it off here. All right, so I'm going to leave this as is because this is a design that we created. And what I'd like to point out is when we created that design, we checked this option right here. Now what it says is to write the MDM generated model parameters to all lower levels. What that's going to do is it's going to find out your leakage resist or your leakage inductance and your resistances and populate them here in this level right here. Same thing with your magnetizing inductance on all levels, right? So all of these levels should match this model level 3 because they were created using MDM. All right, so we're going to create and use MDM and run this simulation. All right, and they pretty close. There are some little bit of differences here, but it's because we're using a much more accurate model. All right, so that's cool, but one thing to mention, another great feature of MDM is that it can also calculate detailed and accurate inductor and transformer losses and temperatures. The way to do that is we're going to open this dialog back up and activate this next button or this next option here. So this is the power probe calculates detailed losses and temperatures using a post process. All right, so I'm going to turn that on. Press OK, and one last thing we have to do is we have to drop a probe, a power probe, onto any one of these pins of the transformer. So I'm going to just drop it on our top primary pin, and I'm going to run the simulation one more time. Now it won't change anything electrical, but what you'll see afterwards is now we calculate all of the total losses. All right, so you can see it's broken up here. This is the overview. It breaks it up by our winding losses and core losses. And then you can actually even look by winding where the transformer is losing the most energy or most power. This will give you all the graphical data or the waveforms, such as your flux density, your currents, and the flux density, the currents through each of your windings, and the voltages on each of your windings. And then this will give you your inductance versus current, what we placed in the magnetizing inductance here. And then finally, it'll give you a overall transformer design output, if you will, like a report. A lot of good information there. All right. Getting close to our end. So we're going to talk one more item, which let me go ahead and close this, not that. And final item we're going to talk about is the C-code DLL defined digital devices. Now these devices are your digital code written in C or C++ running directly in SIMPLIS. Because there are no gates to layout, the implementation can be very quick. And because the simulation is not a co-simulation, the simulation will be just as fast as your normal SIMPLIS simulations. Very, very powerful. Now, there are a few requirements for this. This will come prepackaged in SIMPLIS Pro or Elite. It is not available on the Basic. And this is, or the, excuse me, the Classic, we call. Now, the functionality will be made available automatically. No additional costs are necessary. You will require a compiler tool chain like a Visual Studio's. And then there is the requirement of a SIMPLIS digital development kit that includes some header files, documentation, and some other examples. But we are working on kind of eliminating that requirements that we'll talk about in the actual webinar in 3 months. So let's go ahead and take a quick look at an example. So what we're looking at here is a variable frequency source, basically a voltage controlled source. And what we have here, this is a digital signal source, and all it's doing is basically creating a switch case, if you're familiar with programming. So what this is going to do is it's going to tell our lookup tables, 2 lookup tables, whether it's a case number 0, 1, 2, or 3. All right, now the top here, based on the input 0, 1, 2, or 3, it's going to give a decimal output of 1, 20, 300, or 4,000. And we'll talk about what that means here in a second. And that gets fed out into the base input of the frequency generator. And then finally, we have at the bottom is a decimal output of either 3, 2, 1, or 0. And what that's going to do, that's going to feed into the exponent. Okay. So what does that mean? All right. So this frequency, the variable frequency digital source, is going to take these 2 inputs, the base and the exponent, and then the frequency output, or the output, is going to be derived by this equation. Right. It's going to be the base number times 10 raised to the exponent. All right, so let's go ahead and run the simulation because it's easier to see that way. So if the select pin, or this select option right here, was 0, that means the base value was 1, and then the exponent was 3. So if we take now and do base 1 times 10 to the 3, we should have a 1 kilohertz voltage, frequency. Now we do in blue, our green is the output of our source, and then the blue is just a 1 kilohertz reference signal. So if we compare this first section here, we notice that we have a 1:1 ratio for the 1 kilohertz reference. Okay, so we now see that it is 1 kilohertz. Now, if we move to the next section, which is here, our select went to 1, and move back here, our base was 20, and our exponent was 2. So now we should see 20 times 10 to the 2, which should give us 2 kilohertz. Now, if we compare this output to our 1 kilohertz, we notice that for every 1 cycle, we see 2 cycles. So that is a 2 kilohertz output. Next, we should see now, we come here. This is a 300 base times 10 to the 1, which should give us 3 kilohertz. Now, if we look at 1 switching cycle, or 1 cycle here, we see 1, 2, 3, which is 3 kilohertz. Then finally, if we come to our last section, our middle section here, we have 4,000 as the base times 10 to the 0, which means it's 4 kilohertz. For every 1 cycle, we see 1, 2, 3, 4. So that's one. This is just a way if you had a predefined set of, let's say, frequencies, or a predefined set of some variable, you could go through them using this type of iteration here and just an easy way to show. Now we are getting towards the end, so we are not going to go over any type of coding for this. That will be covered either in the a separate video or a separate webinar. We don't want to weigh down any coding type of questions here. So I don't see any more questions or any at all. Please feel free to enter them in now if you have any questions. I'll just go ahead and recap and then check back with you guys. So major overview of, overview of the major items for SIMetrix SIMPLIS version 8.4 were the capacitor or inductor conversion tool, the addition of the power supply sources and loads, a couple useful schematic editor features, the updating of the controlled sources with ideal limiting, the addition of the multi-level Lossy transformer, and the major items of the magnetics design module and the C code DLL defined.
Unmuted.
So now is the time, I think. If you have any questions, please feel free to send them in. We'll do our best to answer them. So I see there are a couple MDM questions. These will, we're going to hold off on these. And if you do send an MDM question in, we will follow up with you. But because there are actually three more webinars coming up with that, most of your questions should be answered with those. So if you have an MDM question, feel free to send it in. But we will we'll just save those for the future webinars as well. But you will get an answer if you do a separate follow-up answer with those. One question I see is version 8.4 already available for download? Yes, it is. It was released back in May, about a month ago now, so that is available. And if you need any help getting the download, feel free to email us at support@simplis.com, or you can find out more information on our website.